Okay. Let's move on and do number 10. All right. So starting with number 10, it says that I have apparent weightlessness of a passenger can be created for a brief instant when a plane flies over the top of a vertical circle. So there's my vertical circle. My radius is what I'm looking for. My speed is 420 meters per second, I think. Okay, so now for that passenger to appear weightless, I have to have no force normal pushing on the passenger's body. So I just have gravity pulling it inward and letting that equal to mv squared over r. So the masses will cancel. So I'm looking for r, so r is going to be v squared over g. And again, they don't give you much information because you don't really need it. So 420 meters per second. Don't forget to square it and divide by 9.8. So when I did that, I got the radius to be 18,000 meters. Okay, number 11. Number 11 says that we need to find the maximum speed with which an automobile can round a curve at 80-meter radius without slipping off the road. The road is unbanked, and so the only thing keeping it on the road is the friction. So net F equals ma. So my net force is friction. It's moving in a circle, so A is going to be a centripetal acceleration. So friction is mu times force normal. Well, force normal is just the weight because I'm on an unbanked road. So I don't have to worry about any slopes or weird force normals. So I'm looking for the radius of the curve. So the radius is going to be v squared over mu rg. I'm sorry, I didn't do that right. It's going to be v squared over mu g because I've got the radius already moved to the left-hand side. So the radius is going to be, well, my speed that my passenger wants to travel at is what I'm looking for. Sheesh, I'm not having much fun. So I wanted v squared is equal to mu rg. Mu is 0.81. The radius of the road is 80 meters. And gravity is 9.8 meters per second squared. So I want the square root of that. So v is going to be equal to that value. Well, when I take the square root of that, I got 25.2 meters per second for the maximum speed that I can safely maintain on that curve. All right, number 12. Number 12 says we have a satellite going around Jupiter, and we want to find the orbital speed, and they give us all kinds of data. Okay, so there's my givens. They give me the mass of Jupiter and the radius of the orbit, well, how far it is above Jupiter, plus I have to include the distance from the center of Jupiter to the surface of Jupiter, and they want me to find the orbital speed. So I said, well, big G m1 m2 over r squared is equal to mv squared over r. It doesn't matter which mass. I'm going to call it mass 2, so it'll cancel out. And that'll cancel, and I'll have one of those over there. So v is going to be the square root of 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. And my mass of Jupiter is 1.9 times 10 to the 27th kilograms. And my r is going to be the sum of those two numbers. And when I summed it up, I got 1.43 times 10 to the 7th meters. So I'm going to solve for my velocity. And when I solved for my velocity, I got 42,129.9. Or, let's see if I added those. Actually, I'd like to just use this number, a different one here, because when I added them, I should have gotten a little bit different than what I wrote down. So let's see. That's 6 times 10 to the 8th. Yeah, I'm going to get 6.714 times 10 to the 8th meters, I believe. Let me double check that. Yeah. And when I did that, I got the speed to be 13,738 meters per second. That's my speed of my satellite around Jupiter. Okay, on number 13, they've given me a list of givens, and they want me to find the orbital speed of a satellite just above the surface of the moon, and then the period of that same satellite. So I said, well, big G m1 m2 over r squared is equal to the mass of the satellite, so I'm going to call that 2, v squared over r. Cancel, 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 cancel. So v is going to be the square root of big G times the mass of the moon all over the distance from the center of the Earth to where the satellite is located, which is 1.74 times 10 to the 6th meters. So my speed is going to be the square root of all of that stuff, and when I did that, I got 1,678.54 meters per second. And then now they want the period. So v is equal to 2 pi r over t, or t is equal to 2 pi r over v. And I know that I have 2 pi, and my r is going to be 1.74 times 10 to the 6th meters. And my velocity I figured was 1,678.54 meters per second. So when I did that correctly, I got t to be 6,513.2 seconds, which works out to be right at 2 hours. Okay, we have one left to go. Number 14. Okay, so I have my list given. So I said, well, big G, mass of the satellite, mass of the Earth, over r squared is equal to the mass of the satellite, speed of the satellite, over r, very similar to what I've done before. Satellite mass cancels out. So I said, okay, well, big G, mass of the Earth, over r is equal to the speed. Well, the speed is going to be, and that should be v squared right there. The speed is going to be 2 pi r over t, but I got to square that. So that's going to be 4 pi squared r squared over t squared. And I think they're asking me to find t, so I'm just going to do a little bit of math. So I'm going to say, well, t squared is equal to 4 pi squared r cubed over big G, mass of the Earth. I want t, not t squared, so I'm going to take the square root of both sides, so that's not a big deal. We know how to do that. So t is going to be equal to the square root of 4 pi squared. R was my 8 times 10 to the 6th meters. I'm going to cube that. And then I want to divide it by 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. And my mass of the Earth is 5.98 times 10 to the 24th kilograms. So when I did all of that, I got my period to be 7,120 seconds, which is very close to 2 hours.